Greetings and welcome. Last night we were talking about, or yesterday, we were talking about the complex plane and polar form of complex numbers. The homework I'm looking at is on page 590. And I'm just going to go over a handful of problems, explain them to you. So here's question 17. It says solve each equation for x and y where x and y are real numbers. So that's kind of nice that they restricted it there for us. So if I've got these two now, x and y are real numbers, but these entire expressions on each side happen to be complex numbers. And if these complex numbers are actually equal, then that means the two real parts are equal, so 1 must equal y, and the two imaginary parts must be equal, so x plus y must equal 3x. So once I've kind of simplified it down to that point, it's just a matter of now solving this using substitution or whatever way I want. So for instance here, if y is equal to 1, I could then substitute that in over here, and I'd have x plus 1 equals 3x. Subtract an x from both sides. Oh man, I can't get away from that too. I'm preemptively calculating it there apparently. And then I get 2x equals 1, divide both sides by 2, and I get x equals a half, and as previously stated, y equals 1. So it's just a matter of writing both of these in rectangular form, set their corresponding parts, the a is equal and the b is equal, essentially is what we're doing there. Question 23, it says graph each number in the complex plane and find its absolute value. Another name for the absolute value here was called the modulus. And this formula wasn't too crazy to find the absolute value, but let's graph it first. So just so you're aware, this is the x-axis or the real axis. This is the I-axis or the imaginary axis. So in order to graph this, I would go left 1 and then up the square root of 5. Square root of 5 is going to be bigger than 2, less than 3. We might as well get a decimal approximation of it while we're at it. Let's see, square root of 5 is 2.236. So left 1 up 2.236. Somewhere right there is where I would find that, right? So I went that distance and that distance. So if I want to find the modulus of this, that's essentially just the hypotenuse of this little right triangle. But you can actually use a little formula for that. The modulus of this complex number is the square root of a squared plus b squared. This is just straight up Pythagorean theorem. So this is going to so the modulus is equal to the square root of -1 all squared plus the square root of 5 all squared equals the square root of 1 plus 5 equals the square root of 6. And I believe that is the answer that the book had. And so the square root of 6 would also be this distance there. So that's the idea for problem 23. Just a matter of using that formula and graphing it. Here we go. Express each complex number in polar form. Polar form. So in order to find that, I'm going to need to know what r is. R is the same as the modulus. It's so r is just going to equal the square root of the a squared plus b squared. And I'm going to have to figure out what the amplitude or the argument is. And I actually, I'm more of a fan of using this version. Tan theta is equal to, this would be b over a in this case, in order to solve for theta, right? So I'm going to solve this for theta, but instead of using arctan or tan inverse, I like doing a little bit of the work, the grunt work myself for this. So in order to figure this out, a is equal to -2, b is equal to 4, so that means r must be equal to the square root of -2 all squared plus 4 all squared, which is equal to the square root of 4 plus 16, the square root of 20, which breaks into the square root of 4 times the square root of 5 if I pull out the largest perfect square that goes into it, or 2 roots of 5. So here's the value of r, or the modulus. Tan theta must have equaled 4 over -2. So that means tan theta is equal to -2 when I simplify that. And to solve, I'm going to have to tan inverse both sides. tan inverse. And this is a little bit tricky to figure out. Tan inverse of -2, I can't do that with a hand trick. So I'm going to reach for my calculator. Tell you what, I'm going to do this in degree mode. Let's see, so tan inverse of -2, close parentheses, and I get -63.43. So that means my reference angle, maybe I'll write it that way, is the 63.4349 degrees. Now, if I want to figure out what this theta actually is, I might want to look at where this would have been graphed on the complex plane. Notice it would have been going left 2 and up 4. And of course, tangent is negative in that quadrant because both sine and cosine have different signs in quadrant 2. So I'm interested in an alpha of this value, 63. So that means theta must have been 180 minus alpha. All right, or if I was dealing with radians, I'd do pi minus alpha here. So theta is going to equal 180 and that, which is 116.5650 degrees. If I want that in radian mode, I can just multiply by pi over 180 again, just in case they want theta in radians, which oftentimes these are expressed that way. Math tends to like radians, math students tend to like degrees. But let's see, I'm still not done. It says express each complex number in polar form. So what does this mean in polar form? That means 2 square roots of 5 multiplied by the cosine of 2.0344 plus I times the sine of 2.0344. So this is polar form, or you can use the nice little shorthand 2 roots of 5 multiplied by the CIS, the cosine I sine of 2.0344, if you're a fan of shorthand abbreviations. There you go. One last example here. It says graph each complex number, then express it in rectangular form. This actually is much easier conversion typically. So let's see, the modulus is 2. My angle is 4 pi over 3, a little bit more than a pi. So 4 pi over 3, let's see, here's pi over 3 is like 60 degrees. So 4 of those is going to actually land me greater than pi. I believe that lands me all the way down here. It's 4 pi over 3. And if the radius is 2, then I'd go out 2 units. And this is where that point would be. All right? Right there. It's technically just the point. It's still the complex plane. I've still got I-axis and real axis, stuff like that. So now if I want to convert this, all I have to do is calculate the value of cosine and sine. Cosine is negative in that quadrant. The reference angle is pi over 3. Plus I times sine is negative in that quadrant, so that's negative sine of the same reference angle. And so I'm going to have 2 times the negative, let's see, cosine of pi over 3, if I'm not mistaken, is a half, and minus sine of pi over 3 is root 3 over 2 times I. And then I just distribute here, so I'm going to have -1 minus the square root of 3 times I. Be careful that your radical vinculum there doesn't go too far. And that's what we've got, so not that bad. So that means that rectangularly speaking, the equivalent of this is going left 1 and down the square root of 3 would give me the same point. And in fact, it does. Thanks for watching, Internet friends. Have a great day. Bye-bye.